So let's start with a very, very basic question. So what is the universe made of? So we know that the universe is made of atoms, but these atoms are at the same time based on what we call the elementary particles. The model that we assume is the one that works, and the official we use is called the standard model. This is a huge, well, actually not huge, it's a small zoo of particles called, so you have the quarks, you have the leptons. There's one here that you may know, it's called the electron. You may have heard about these ones and neutrinos, that they're related to some Nobel Prizes. Actually, this last Nobel Prize was awarded to, the physics Nobel Prize was awarded to neutrino work. So let's focus on the proton here. So the proton has particular substructure. Is composed of 3 of these little particles called quarks, the one here. So they are like the most basic bricks of the universe, as far as we know. So you know that these particles, they have some basic properties like mass and charge and weird stuff. And there's a particular property we are interested in, it's called the spin. So maybe you know from basic physics that there's a property called classical angular momentum. It's a quantity associated to rotation. Something happens very similar with quantum physics. The difference is that here you have discrete levels of this momentum. So the spin is a type of angular momentum, but you can imagine these are like particles with this vector pointing somewhere in space. And we usually say this is just an intrinsic property of the particles. And well, there's a fun story about this because like the mid-20s, this theory was postulated by students at MFest. By Uhlenbeck and Goldsmith. Ehrenfest was their advisor, and he suggested that they should risk publication of this theory because they didn't have any reputation to destroy, so just go ahead and... so yeah, this idea was first rejected by physicists that there's this intrinsic thing related to something that is not directly, it's not related to rotation as the regular angular momentum. So this just comes from nowhere. But this is so, if you're interested in more in this, there's a very interesting paper here that discusses that idea that actually the spin is really intrinsic. Here they argue that it's more related to the electron wave field, and this applies to all kind of particles and is consistent with quantum mechanics. But we don't have to go deeper into that because this is more about this here. So this is that nuclear magnetic resonance. This is a type of experiment that involves the detailed manipulation of nuclear spin. So we have these particles, and we have this property of the particles, the spin. And with the nuclear magnetic resonance, we can interact with this property and get information about the data. So here you can see a NMR machine, so nuclear magnetic resonance. We are going to call that just NMR for simplicity. This is they are like big machines, and you may have seen these machines at the hospital. They are basically the same thing. They are usually called MRI machines. So what is NMR good for? So maybe you have seen this show CSI where they have I don't know, they find a dead body. So a lot of guys like get blood samples and they find liquids. So they go to this fancy lab with pretty girls in coats. They put the fluids in the machine, and they say, oh yeah, this guy was killed by the venom of the Peruvian shushup snake. Yeah, maybe they're right, and finally they get the killer. So anyway, so those machines there, what they are doing is identifying these things they got from the body, but how do they do that? They use a lot of different techniques. So in this case, the NMR is good for organic materials like, I don't know, like a cat or a flower or bacteria or something like that. So in this case, the organic materials have they have convenient magnetic properties related to this spin thing, the spin properties. So the NMR is good to use to be used on organic things. So how does NMR spectra look like? So spectra is actually the plural form of a spectrum. So you can see here, it looks like someone sneezed on the screen, but they didn't. You see these spots, but they actually mean something. So here we are looking at specifically molecule. It's called histidine. And the interesting thing here is that you can see a network of things connected in this spot. So just for you to have a clear idea of what you are seeing here, you are actually seeing a 2D part of the 3D spectrum, so something like this. At a very particular zoom, I can zoom in or zoom out of the data, so you are just seeing a planar view of the thing here. So, well, you can see the formula here, and actually the structure diagram. I'm using our actual Wolfram language to get all this information here, and it's actually pretty cool because you can get these nice graphs from a lot of molecules. And actually, let me risk and try something else. This is a nice molecule. It's a kind of gruesome molecule related to the stench in corpses. That's what it's called, cadaverine. Is that the name? Oh no. Let me see what's the name of this. Right. All right, maybe work one day. So anyway, we can get all this stuff from oh, here it is. Good. So yeah, we're getting all these from the actual Wolfram language. So what I want you to see here is that what we are interested in is these carbons. This is the actual molecule and the representation of the molecule. And I've numbered these carbons here because they are directly connected. You have another carbon here, but I didn't put a number there because it's not directly connected to the carbons. But in this particular case, the experiment we are using just is focusing on this type of connected carbon. So it's kind of beautiful here that you can see that the connection in the diagram is actually represented in the weird spots you can see in the spectrum. All right, so here comes the mathematical part. So what's the idea of this? So again, we have this spectra that we collect from organic samples or whatever. And what we want to know is what's there. I mean, we get something from a plant or from an animal. I want to know what it's composed of. So there's the idea of all these using Mathematica to create a database and compare all our spectra and try to find out what's in here. So basically what the software does is, so remember this is a 2D version of the whole 3D structure. I didn't plot the 3D thing because it's like a lot of data and my machine will hang up if I try that. But basically what I do here is I start going deeper and deeper and deeper into the data. If you go deeper into the data, you get more information, but at the same time, you get more noise. So it's a push and pull thing that you have to deal with both stuff. So basically, I start going deeper into the data and eventually get all the results together, like here. So you see that there are like overlaid peaks all over the place. And when I have all this data, I just run some filters to just remove the noise and get the data I want, like here. So there are some theoretical aspects of all this that that they have to occur. So at least I know a little bit what I'm looking for. So anyway, after running all the filters and having all these cool data here, I'm finding a network. So remember, these networks are actually representing these connected carbons in the molecule, but it's not a perfect one here. Actually, this is real data. I mean, this histidine molecule Spectra was acquired at the University of Florida labs, and it's a beautiful Spectra. I mean, you don't have too much noise and stuff here and artifacts. So that's, but the software, if you see it's getting like a lot of networks and stuff, but it should be smart enough to discriminate and understand which networks are worth it. So I use the BMRB database to create from they have just one-dimensional data, and I use this to create a two-dimensional data database of reference spectrum. So, all right. So let's try here. Just first a simple example of what is happening here. So this may take a while to load. All right, so the thing here, this GUI is just running all the steps I show you, but just in an automatic way. And the thing here is that we want to share this with the scientific community. So the scientific community, they want like buttons and text fields and things where they can insert data and press stuff and get information. So yes, with these buttons, I'm just running and getting all the things I just mentioned. So in this case, this is just one molecule. This is just a very simple example. I have a more complex one. So I'm just getting a network. It's not a perfect network, but it may give Mathematica an idea of what to look for. So like I said, I made a database of all these reference spectrum where I have, I don't quite remember, but I have like, I don't know, 2,000 or 3,000 of reference spectra. So the idea is that, here we go. We also have like different filters to discriminate the artifacts and noise. So do you remember I said that this was a histidine molecule? So we have all our candidates here for identification, and yay, I mean, this one is the first one, so it's good. So I have a more complex one after this, but let me, so how are we doing time? Let's leave this for the ending because it may take a while to load all the stuff. So what's the workflow summary of all this? So we start with an animal or something we want to analyze, and so we get a sample from that. We put this in this machine here, and this machine here works with this spin property. And eventually we go to the Wolfram language, and the Wolfram language will do all the hard work for us to identify this unknown stuff we have there. So our future plan here is to deploy this to the Wolfram cloud, because as I said, we want to share all this with the scientific community. And so, well, a problem we still have to tackle is that these are very, very big files. So we'll still have to deal with that to make a good deployment to the cloud. And actually, so I've seen the conferences these days, and I'm wondering if we can, I don't know, we can maybe use machine learning or that kind of stuff into teaching this software to look for patterns and be smarter. So I have to mention so this was made with the Edison Lab at the University of Florida. These are the guys I have to thank, and of course also I have to thank people from Wolfram, especially Francisco, who is, well, he always helps us. This has been published here at the Analytical Chemistry Journal. So we still have, I think, like 2 minutes for a complex demo here. So this may take like a minute or something to load. So you can, while this loads, if you have questions, just go ahead. This may take a little while. But the idea here is that, so well, it's more a philosophical view that we don't actually fully understand how nature works, or why is it like it is. But we at least understand the rules, and here are the rules are what we are using here in Mathematica to try to analyze all this. Basically, what's new about this is that people usually in this field, what they do is do this by hand, so they have like their spectrum and they overlay other kind of spectrum. Yeah?
So as I understand, each carbon-carbon pair is represented by 2 dots in the horizontal line.
Right.
And this left line goes to the center. What's that?
Second?
Line
That diagonal line?
Yeah.
Yes, it's just that it's a diagonal line, because in this kind of experiment you have like equidistance between the carbons there. They are equidistant, so I just put there to show that you have to fulfill that theoretical.
So from the spectrum you can determine how this carbon is organized. What's the chain?
Right? Yeah, I mean, we can also eventually, from here, find out the topology of the whole molecule. And that will be a nice update for that. But so in this case, I'm using the first example I did was just one molecule. This one has like, I don't know, like 15 or something different molecules here. So it may take a while to load. So what is loading? Anyone has any more questions? Oh, here we go. So the script is finding like a lot of stuff, and now comes the fun part of looking for interesting networks. So in this case, it can find like, so these one are boring ones, but here comes some more interesting ones, right? So here we are just saying, okay, there are networks here, but we don't know what they are. So let's query the database. And try to see if it succeeds. Oops. So again, this is a project done separately from Wolfram, but I see like a lot of potential of including this type of stuff in our language. So I hope we can do that eventually. All right. All right, so we are getting like a lot of results here. Let's just run a last filter. And we can also create like a nice report of all the stuff. Okay, so here we get the summary of all these identified compounds. The cool ones are here. So you see this. Yep. So you see here this kind of well-matched compounds. Well, I know they're well-matched because I know the data, but you don't. But I can show you that. So we have also a little tool here to. So this is most like most people do this. They don't have an automated way to do to find this kind of networks and identify compounds in this kind of experiment. So I think maybe network 7. All right, so here just to compare the results we find with the actual theoretical values and the stuff we got from our database, we have this little tool where you can, so these, so the carbons I was talking about, so these labels here correspond to the actual theoretical ones, and you can see that they perfectly match the network. So this one did a good job. You can compare that to another candidates that had a lower probability, and you can see that they don't match as good as the other ones. Yep.
So this, on this diagram, basically, so you found one network. What about other peaks? Is that other molecules?
You mean the other networks?
The other, so you identify several peaks that
Yeah.
form the molecule for carbon.
Right.
What about the other peaks? Is that other, do they correspond to other?
Yeah, but they are not part of that network. So let's say we can try this one here. So this is another network with another peaks, and I don't know if this did a good job, probably. But yeah, some other peaks here correspond to other networks, maybe.
So one diagram gives you
Right. Yeah, some of that. So usually,
The other thing is you have isotopes in there, right? You probably don't have a clean isotope thing. You have C14, C13, everything. You will then see chemical shifts in this spectrum as well.
yep. Yeah, usually get a lot of noise from like the solvents and the machine itself.
So do you have do you have intensity for the spectra as well? It's not the case, right?
Say again, sorry.
Do you have intensity of in this case you could say, which are dominant ones, right?
Yeah. So, like I said, I don't remember quite well, but I think this mixture has like 20 compounds or something, and this one detect 10. So it basically takes from the paper, we got that it gets around 60% of the networks. So, I mean, it's a useful number.
I remember that from my studies. There were a lot of peaks.
Yeah. So yeah, I'm wondering. Like I said, I see the other conference where they do they use machine learning to identify pictures and stuff. So this is more a question for me or for you. That can we use that kind of technology to train the software to look for this stuff? I don't know. I hope we can. Well, I think that's it.